All right. So we have, well, let me see who we have. Abigail. Gotcha. Abigail is here. Kincaid is not here yet. Andrea is here. Mullins is here. Lewis is here. Cooper isn't. Cooper is here. Hunter is here. Both Meltons are here. Crowder is here. Reinhardt is here. Julia, not here yet. Rogers, not here yet. Talbert, here. Kennedy's here. I think we have everybody. Kylie's not here yet. Larissa's not here yet. Madeline is here. Hughes is here. Galloway is not here yet. Cook is here. Durgan is here. Tate is here. Burton is online. Kinder, not here. Jones is here. Canterbury, not here. Tristan is online. Hobson, not here. Ray is not here. And Fisher is here. We've got about a minute, and we are recording, so I'll do reminders. So I guess I'll just start off with good news. It's more of an announcement than a reminder. So once again, you guys, this is probably, excuse me, man, I can't speak. Still waking up. Probably the best start to a semester I've seen. Not just you guys, but also my online courses. So I'm really excited about that. However, that just means I have more work than usual because usually people aren't turning in their assignments on time or they're not turning in their independent work yet. So I'm busier than usual, which is why I'm slower than usual. So I wanted to apologize for being slow to grade and to respond to emails, but that's why. So keep up the good work. Speaking of independent work, as of last night, you should have 10 points of independent work, at least, right? And then by a week from today, you should have 20 points. Any questions with that? Remember, just write papers, turn them in. You can write a 2-sentence paper or a 2-page paper or a 20-page paper, whatever. It doesn't matter, right? It doesn't matter how long your paper is. Just the longer it is, the more it's worth. So write as many papers as you need to do to get to those 10 points if you haven't already, and then to get to your 20 points by Sunday. So any questions about independent work? Galloway? No, last name? What is it? Hobson, yeah. Hobson is here. All right. What else? Lab 1 should be done. There's still a couple that I need to grade. And again, you guys are really good. So a lot of you have already graded it. And I left feedback and said, you could fix this, you could fix that. Usually people just keep their grade and say, well, it is what it is. But you guys, for the most part, have been responding to those. So again, I have a lot more grading to do because I have a lot of regrading because you guys are on the ball. So really good on that. But yes, you should be done with Lab 1. That should have been done by Friday. You should have the pre-lab done for Lab 2 by last night. And I hope to get those graded today before we get to class or get to lab. I guess that's it. Any other questions or any questions at all about lab or independent work? All right. I'm really guessing here, but I would assume the exam will be sometime next week. But I'm really just guessing. I'll let you know a little bit more on Wednesday. And then, as I usually do, I'll probably put it up to a vote. So the specifics of when it's going to be is going to be a group decision. Well, any questions about anything? All right, we had some people come in. Hold on, I know this. Hannah? All right. So anybody I didn't call for, oh yeah, Drew. Hold on, I read this too. Larissa. Okay. Everybody's accounted for. So the first word for attendance, well, let me pull this up first. The first word for attendance, I'll just write it. No. I've underlined it. Of course, that's misspelled, but First word will be formal. So for those of you in person, you can send me these words sometimes before 9 a.m. to get the extra credit, the little bit of extra credit. For those of you online, send me that word, the words in one email sometime before 9 a.m. to get your regular credit. And if you're watching the video later today or whenever, instead of sending me the picture formal, or excuse me, the word formal, send a picture, a screenshot of me pointing at the word formal. There you go. Anyway, let's jump into it. This is where we left off. We left off talking about covalent bonds. We've already talked about ionic bonds. Those were the first bonds we talked about. Ionic bonds, to remind you, are when an atom gives up an electron and becomes charged, or it gets an electron and becomes charged. And because they're charged, they're attracted to each other, right? So ionic bonds are when they give up electrons and become charged, right? They become ions. Then we talked about covalent bonds. This is the last thing we talked about. The most important thing you need to know about covalent bonds are that that's when you're sharing electrons as opposed to giving them up or taking them, and that they're the strongest, right? So this is, again, a very important bullet point. And then I think what we left off was talking about this idea of polar versus nonpolar. And like I said, last time we talked, nonpolar bonds are when our electrons are shared equally. Polar bonds are when they're shared unequally, but we'll come back to that discussion. I'm pretty sure that's where we left off. But just in case, does anybody remember if I gave you this example, the carbon example? Even if I did, it won't hurt to talk about it one more time because this is what you're going to need to do in lab. This is one of the things you need to do in lab. Matter of fact, you can get a head start if you want and go ahead and do this portion. You guys have all seen the lab, so you know that little table? Well, anyway, this is how you're going to do that for the table. Here's what it is. It'll say carbon. So you look up at the periodic table and see, okay, carbon's atomic number is 6. If its atomic number is 6, that means we know it has 6 what? It's a good review. Good. 6 protons. That's what the atomic number means. That means how many it has, the number of protons it has. Yes, it has 6 protons. And since I haven't said anything about it having a charge, how many electrons must it have? It doesn't have a charge. It's neutral. So it has 6 protons and a neutral charge. So how many electrons must it have to balance out the 6 protons? Those 6 positive charges. Good, right? 6 electrons. Perfect. So we know it has 6 electrons. Then we draw it. Of course, it's already drawn here. We know that the first ring holds 2. So we would draw that and write our first 2 electrons. And then we'd realize we still have 4 electrons left to deal with. So we draw another ring and we draw the rest of the 4 electrons. Does that part make sense? You can see that all 6 electrons are accounted for. You can see that the first ring is full. Then you can see that the outer ring only has 1, 2, 3, 4 electrons. But how many can the outer ring hold? Good, 8. How many of you guys remember this already? Yes, 8. It can hold 8, but there's only 4. So if it needs 8, but it only has 4, then how many more does it need? 4. Good. All right, we already talked about that. It has 6 electrons, 2 on the inside, 4 on the outside. Therefore, it needs 4 more to fill the outer shell. And here's the important part for you guys. That means it can bond 4 times. Now, I'm only going to put a big X to this to indicate this will not be on, well, I'll put a big question mark. This probably won't be on the exam. The reason I included this in such detail is because this is what you're going to be doing in lab. So this is more of a lab thing than an exam thing. And it wouldn't hurt in lab to memorize the fact that carbon can bond 4 times. But again, I'm not going to ask you that on the exam. Actually, I'll never ask you how many. I probably won't ask you how many times carbon can bond. I'm going to put a question mark next to that too. I don't like the word never. But anyway, are there any questions about this example? So again, in lab, you're going to be doing this with the other ones, right? That's how we do carbon. We can do the same thing for hydrogen, oxygen, nitrogen, I think phosphorus maybe. Anyway, that's how it works. If there's no questions, we'll move forward. Here's some pictures of some more examples. This is the same molecule. This is formaldehyde. And there's different ways of drawing it. This is the one you should be familiar with. Not for the exam, but because almost every time I show molecules in this course, they're going to be that version. So you should be familiar with looking at them and understanding. So here we have carbon. Like I said, it can bond 4 times. So that's 1 bond, and this is a double bond. So that's basically 2 bonds, right? So it has 4 bonds. Oxygen can bond twice. You learn about that in lab. Hydrogen can bond 1 time. You learn about that in lab. So another reason this is important is not for the exam, but for lab, again, is these are the kinds of things you're going to be drawing in lab today or Wednesday. So not only will you need to do the table that we just talked about, where you figure out how many protons it has, therefore how many electrons, therefore how many times it can bond, but you're also going to be giving a molecule, and you have to draw it. So in this case, and it's, oh yeah, it is up there. See, in the lab, you get this right here. You get the molecular formula, in this case, CH2O, and then you have to draw it. Now, I would ask if you have questions, but lab would be the better place to take those questions about this. So for now, we'll just move forward. Also, I'll point out that's just an example. I'm not going to ask you any questions about formaldehyde. And formaldehyde, as far as we're concerned in this course, is not an important molecule. Some of these other molecules will come back. All right, if you download the PowerPoint, you can see this animation that shows what a covalent bond looks like when it forms. Here we go, back to this idea of polar molecules. Like I said, there's polar molecules, there's nonpolar molecules. Nonpolar molecules are when the electrons are shared evenly in the covalent bond. Polar molecules are when they are not shared equally. So, let me ask you this. Well, I'll just tell you. If you look up the table of periodic table, I'm sure you can't see it from here, but hydrogen, its atomic number is 1. Right? Hydrogen's atomic number is 1. Not that you need to know that. But if its atomic number is 1, how many protons does hydrogen have? Good, right? So I'm just going to write 1p. I'll just draw a p there. I hate it when it does that. Yeah, so hydrogen has that 1 proton. Oxygen's number is 8. So how many protons does it have? Good, it has 8 protons. Try to draw that. That looks like garbage, but whatever. You can see it's there. So this thing has 8 protons. This one only has 1. This one has 1. What charge do protons have? I think someone said it. I think a few people said it. What is it? Good. They have a positive charge. And what charge are electrons? Yes. Electrons are negative. Therefore, we know electrons are attracted to protons, right? Because they're positive. Protons are positive, electrons are negative. They're attracted to each other. So if you're an electron who's attracted to protons, where are you going to hang out? Where would be your number 1 choice to hang out the most? Would you rather hang out with A, the hydrogens, or B, the oxygen? If you are an electron and you're negative and you're attracted to positive things, where would you want to hang out? The oxygen, good, right? Because the oxygen's got so many electrons. But then it's going to go there instead, right? And that's why we have polar bonds. Yes, it's a covalent bond. Yes, they're technically sharing electrons, but they don't share them equally. So using this example, and this is the best example because this will be important later, the fact that water is polar. But yeah, so the electrons are hanging out more towards this end of the molecule, more towards the oxygen end. Therefore, when you look at water, it's partially negative. It's partially negative on that side, and partially positive on that side. Make sense? Now, there's a way to draw a partial symbol, but in this course, it doesn't really matter. And as you can see, drawing on this thing is kind of difficult. Anyway, that's why polar molecules are polar, and that will be important later. Throughout the semester, the idea of this polar molecules will be important to come back. So any questions about this slide? All right. So the fact that water is a polar molecule, among other things, results in a weak attraction between neighboring water molecules. So this will definitely be 2 test questions. And I would say historically a majority of the people miss this because there's 2 questions that are similar. And I'm telling you now that they're similar, and I'm warning you not to mess it up. But people will. So if we're talking about water molecules, plural, multiple water molecules, even though you can't see it here, we only have 1 water molecule. But if you could picture multiple water molecules on the screen, the attraction between them is a hydrogen bond. You need to know that, right? There will be a test question that says it's describing the situation, and it's describing the fact that there's multiple water molecules, right? And it'll ask what kind of bond is between them, and the answer is hydrogen bonds. Then there'll be another similarly worded question that's talking about the one oxygen molecule, the one water molecule, like you see here, just the one. And that question will ask what's holding the oxygen and the hydrogens together. And that is a covalent bond, right? So it's a covalent bond that holds this one water molecule together. But if we were to talk about multiple water molecules, those are hydrogen bonds. Any questions about that concept? I'm not done with the side yet, but any questions about that concept? All right, so again, those are hydrogen bonds. And that's the last of the bonds that we're going to talk about. We've already talked about them all now. We've talked about ionic bonds, covalent bonds, and hydrogen bonds. And another thing you need to know, and this will almost definitely be a test question, and it will be important later in the semester, hydrogen bonds are the weakest of the bonds. So you now know that covalent bonds are the strongest, hydrogen are the weakest. Of course, by default, that means the ionic bonds are right there in the middle. But anyway, any questions so far about hydrogen bonds? We're going to talk a little bit more about them. All right, so here's what I mean. Now we can see these hydrogen bonds because we're talking about multiple water molecules instead of just one. But again, if we're talking about just this one water molecule, you can see that it's covalent bonds that are keeping these hydrogens and the oxygen together, right? But if we're talking about multiple water molecules, it's the hydrogen bond that keeps them together. Speaking of which, another thing you need to know, not that I'm going to test you on it, but so you know what you're looking at when you see it. When you see a dotted line, that is a hydrogen bond. So when we're drawing molecules, if you see a dotted line, that is a hydrogen bond. Unlike this solid line, right, that indicates a covalent bond. And again, that will be important later. The idea that hydrogen bonds are the weakest of the bonds. And again, the fact that they're dashed like that. Any questions about that slide? All right. Actually, one more thing before we move forward. We already talked about the idea that they're polar, and this is really demonstrated in this picture. Like I said, the oxygen end of the molecule has a slight negative charge to it, right? The hydrogen ends have a slight positive charge to it. So for that reason, the hydrogen end of one molecule is attracted to the oxygen end of the other molecule. There's an interaction there because there's a slight charge. They're not sharing electrons because that would be a covalent bond. They're not giving up electrons or taking them because that would be an ionic bond, but they're just they're just attracted to each other because there's a slight charge. The next word for attendance, I'm going to underline it. I'm not even going to say it. So that's the next word for attendance. Again, if you're here, you can send these words before 9 a.m. for extra credit if you want. If you're online, you need to send that word for your attendance points by 9 a.m. And if you're watching a video, let's see. Yeah, if you're watching a video, just take a screenshot where you can see that that word is underlined and send that screenshot. Anyway, any questions about this? All right. So let's talk about some elements. This is not in your textbook. This is from your old textbook, so I'm going to go through it quickly. These are just some examples. I'm definitely not going to ask you about this, but some examples from your old textbook were carbon, because you all hear about that. Oxygen, we obviously hear a lot about. Potassium, gold. These are all probably elements that you've heard of. Now, carbon and oxygen are very important for this course, and we will come back to that. But anyway, those are just some examples. Like this says, there's 92 naturally occurring elements. I'm also going to put it next to that because I'm not going to ask you that question. This is not a chemistry class. Some of the chemistry is important for biology, and that's the stuff you need to learn, but you don't need to know that. As we've already talked about, each symbol is, well, we haven't talked about this, but there is a symbol. We have talked about that. We didn't talk about the fact that each one is derived from an English, Latin, or German name, and I'll put a big old X to that, again, indicating that I'm not going to ask you this either. So nothing on this slide will be on the exam. This is just an introduction to what you're about to learn. Here's what you do need to know, even though this isn't in your textbook. So if you're a note taker, or even if you're not a note taker, because I'm not, I would write this down at least. I would write something that says something like, there's a slide on here, and he gives information that's not in the textbook, and I'm required to know it for the exam. So here's what you need to know. There's there are 4 elements that make up about 96% of the body. Actually, you know what? I'll put an X to that number. You don't even need to know that number. What you need to know is what I call the big 4. So there will be a test question that says something. I might even word it that way. What are the big four? So most of your body, about 96%, not that you need to know that, but a large majority of your body is made up of oxygen, carbon, hydrogen, and nitrogen. You need to know that. And that is a lot. So even though you don't need to know that number, we can still talk about it, right? About 96%, that's a lot. So that means, and I think this is by weight. Yeah, by weight. So however much you weigh, only 4% of that is anything other than this. And as you can see here, there's 25 elements. Of those 92, we need 25. And of those 25, it's almost entirely these four. Any questions so far? We're going to talk about this a little bit more of it. Are there questions so far? All right, like I said, you do need to know the big four, but I have a feeling that's something you won't even need to study because we're going to talk about them so much. Right, once we get into biological molecules, you're going to keep seeing oxygen, carbon, hydrogen, nitrogen so much. And then in lab, when you draw molecules, you're going to be drawing them mostly with oxygen, carbon, hydrogen, and nitrogen. Actually, no, that's it. All the molecules you draw in lab, off the top of my head, use those four molecules. Excuse me, 4 elements. Any questions about the big four? All right. So let's talk about the other 4%. So if about 96% is the big four, what about the other? And I'm not going to ask you anything about this, but here we go. There might be questions on the study guide. 2 examples from the other 7 elements are calcium and phosphorus. I'm not going to ask you where this stuff, I'm definitely not going to ask you, but calcium is important for your bones and your teeth, and it's found in dairy products, sardines, and green leafy vegetables. Then we have phosphorus. Whoops. It's a component of DNA, and it's found in eggs, beans, and nuts. So again, those are just 2 examples of the 7 elements that make up the other 4%. Just 2 examples. And I'm not going to ask you, first of all, I'm probably not going to ask you what makes up the other 7. But if I do, I'm definitely not going to ask about these details. Speaking of which, for independent work, if you want to look it up, I'm about to give you the answer, but like I said, there's 7 elements to make up the other 4%. We're only talking about 2. So obviously there's 5 more, right? I'm going to show them to you, but you can look those other 5 up and answer these questions, right? These are the bullet points right here. So why are they important and where can you find them in your diet? For independent work, it's not important for the course, but you can look it up if you want. So anyway, any questions about the other 7? So again, to remind you, there's about 25 elements used in the human body. About 96% of your body is made up of the big 4: carbon, hydrogen, oxygen, nitrogen. And then about 4% is made up of 7 more elements. But think about that. 7 plus 4 is not 25, right? So we still have some unaccounted for elements. And that's where we get this right here. Trace elements. So we also have 14 trace elements. And altogether, all 14 of them makes up less than 0.01% of your weight. I'm not going to ask you that, but that's for your own knowledge, right? That's obviously what the point here is. It's a very small amount. That's why they're called trace elements. And you can look these up. I'm going to give you some examples, and these, again, are just some examples. I'm not going to ask you any specifics about them, but for independent work, again, you can look this up. A good thing to look up with these that I find interesting is dosage, or how do I put it? Toxicity, right? So pretty much everything is a poison. It's just all about the dose. I think it was about this time last year, somebody died, or maybe it was over the summer. Some lady died from drinking too much water, right? She, there was nothing wrong with the water. She just drank too much of it, and it poisoned her. Because everything's a poison. It just depends on the dose. So that's a really good thing to look up, especially considering all the pseudoscience going around and the chemophobia. People will try to scare you and say, ooh, they've got this, they're putting this in the food. I'm like, yeah, well, we need this. And they're like, and somebody might say, for example, where is it at? Fluorine. Fluorine is a poison, and they're correct. Fluorine is a poison. Fluoride is what we put in the water, but you need it in trace amounts. So yes, even though something is poisonous, when you have too much of it, you need it. So again, you can look these things up. Iodine, which was the example there. Fluorine, which is that example. You can look them all up. How much is too much? How much do you need? What happens if you have too much of it? And what happens if you have not enough of it? For any of those 14 trace elements, you can look them up for independent work. But it really is it's an important thing. Because again, fluorine's the big one for me. I hear it all the time from my people who don't know science. The people in my life, like family and friends, like they're poisoning us by putting fluoride in the water. And I just want to tell them, like, well, look it up. Do some research, as you call it. I use quotation marks because they're probably just looking at videos on YouTube. But anyway, any questions about iodine or fluorine? Those are just examples. I won't ask you any questions about them. Here's another great example. I wish we had time. If you download this PowerPoint, you can click this and watch a video. One of these other ones too. This might be a video too. I think if you click that, that's also a link. Anyway, there's two videos, and they're demonstrating the same thing, but one of them's doing it in an educational way, and another one's trying to scare you. But have you ever seen like a cereal box, and you see this on it, where it says iron fortified or something like that? Have you guys ever seen that or heard it, where they say this is fortified with iron? Well, it is, and it's actual iron, and we need it in our body, and it is actual metal, right? Iron, like an iron skillet. So what they've done in these videos, they've taken like cornflakes or whatever it is, it's been fortified with iron. They blended it up with some water, so it's just a homogeneous mix. There's no more flakes. It's just a big mush. And then they took a magnet and they stuck it to the blender, and all the iron from the cereal stuck to the magnet. Could you picture what I'm saying? If not, you can watch the video, but you guys can picture what I'm saying, right? So there's iron in the liquid and it sticks to the magnet. And again, two different videos showing the same thing. So one video is trying to scare you, like they're putting metal shavings into your cereal. It's always they, right? It's a big conspiracy against you, and they are putting iron into your cereal. So this person's trying to scare you about it like it's not a known thing. But then the other person is saying it like the known thing that it is. Like, hey, we put iron in cereal because you need iron in your diet. And then they show the magnet and show you. But anyway, that's just a really good example how people will try to trick you. And sometimes they don't even try to trick you by lying to you. They can just tell you the truth in a scary way. Ooh, there's metal. There's metal in your cereal. And yes, there is, because it's good for you and you need it. Anyway, just an example. I won't ask you anything about that. Same thing here. Iodized salt, right? That's because that means they put iodine in there. We need iodine, so they put it in our salt. Any questions about that? All right. Here's a good little handy study guide, right? So again, what you need to know is the big four: oxygen, hydrogen, nitrogen, carbon. You don't need to know them in that order. You don't need to know their exact percentages. You don't need to know that together they make up about 96%. You just need to know that's the big four. And then there's these. Again, I'm not going to ask you about them on the exam, but this is great independent work topics, right? For all these things. What are they used for? Where can you get it in your diet? How much is too much? How much is not enough? All those things you can look up for independent work. So any questions about that graphic? And again, this graphic is not from your textbook. This is from the old textbook. If you're trying to study and you want this, you have to pull up the PowerPoint. All right, let's talk about water, which will be the next word for attendance. Water. And this time, well, the rest of you just do what you normally do, but this time, if you're watching the video, not live right now, but if you're watching this recording from YouTube, then send me a picture of water. Anyway, let's talk about water. Water. By the end of this section, you will be able to describe the properties of water that are critical to maintaining life. So as I'm sure you know, we need water for life. That's why at the beginning of that first chapter, when I showed you that picture of the Mars rover, we were talking about what are the things that the Mars rover is looking for. One of the things it's looking for is water. Because when you find water, at least we know there's a possibility of life. So let's talk about it here. This is not in your textbook, so I'm definitely not going to ask it. It's a good little introduction. Life began in water, right? So that's the leading theory. And remember, theory is not, that's a big thing, right? That means it's pretty much accepted. But anyway, water started in life, and it evolved there for about 3 billion years before it ever left water. So obviously, that's one of the reasons why water is so important, right? Because life started there. So we're still tied to it. As a matter of fact, and here's one thing you do need to know for the exam. This will almost definitely be on the exam. It is on the study guide. You are made up of about 70 to 95% water. Your cells are. So know that number. 70 to 95. Remember, it's a multiple choice exam, so you'll have at least 3 other choices. And I'm not going to try to be too tricky. Like, so your choices aren't going to be, is it 70 to 95% or is it 70 to 90%? Right? I'm not going to be tricky. It's going to be big differences. 70 to 95 or 60 to 70, right? There'll be whole gaps, nothing overlapping like that. Anyway, yeah, so the abundance of water is a major reason that Earth is habitable, which is really, it's so fascinating when you really look into it, and we really don't have time to, but Earth is just so perfect for life, and slight changes and it wouldn't be. Like, we're really got lucky. Anyway, so it's the polarity and the hydrogen bonds that explain most of water's life-supporting properties. I'm not going to ask you that, so I'll put it next to that. That won't be a question. But when we do talk about all these things that water does, keep in mind that that's the reason, right? It's all about these hydrogen bonds. It's all about the fact that water is polar. It explains everything. And it explains these 4 things. There's no need to write them down. We're going to talk about them separately. But yes, you do need to know this for the exam. The 4 properties of water make it valuable for life. It's cohesive. It moderates temperatures. It floats, and we'll talk about why that's important. And it's a solvent, and I'll explain what a solvent is when we get to that bullet point. But yeah, we're going to talk about all 4 of these separately. So are there any questions so far? All right, let's jump into it then. Cohesion of water. First of all, does anybody know what cohesion means? What does that mean when someone says it's cohesive? How about that? If someone were to describe something as cohesive, what does that mean? What is it? I think we're on the right track. It's when something sticks together. Cohesion is when stuff sticks together, and water sticks together. As we already learned when I first showed you that picture of the water molecules with the hydrogen bonds, right? They stick together. That's what cohesion is. For your own knowledge, not that I'm going to ask you, but adhesion is when something else sticks to something else. So like if you were to get a Post-it note and stick it to the wall, that's adhesion. It's adhesive. There's an adhesive that's making those 2 things stick together. Cohesive is when it's 2 of the same thing. And again, it's due to that hydrogen bonding. So you need to know that. Again, I saw some people writing it down on the previous slide. So yes, cohesion is one of the 4 big reasons water is important. And what is cohesion? It's when the water molecules stick together. Well, technically, it's when any molecules of the same kind stick together. But as far as we're concerned, it's all about the water. There's no other time we're going to talk about cohesion in this course that I can think of. So as far as we're concerned, when you think of cohesion, you should think of water. It's also very strong for water, more than other liquids. So water has more hydrogen bonds, basically, than a lot of other molecules. And that's why it sticks together so well. Unlike, I don't know, alcohol, for example. Alcohol has hydrogen bonds. It's just not as strong. And we'll talk about that later. Anyway, so why is that important? What's it matter? Well, think about trees. Right? Think about a really big, tall tree. And you have to wonder, like, how does the water get up to that tippy top, right? It's not like when it rains, the leaves are catching the water and using it that way, right? It's coming from the roots. So if you're looking at a 200-foot tree, that water somehow has to get from the roots all the way up to that tippy top leaf, right? So that's how it happens. It happens because of cohesion. So you can imagine, right? There's these little microscopic tubes in the tree. And as one of these water molecules evaporates from the top of the tree and it leaves the leaf, then it pulls the other ones with it, like a chain reaction. So that's how it works, right? As water molecules are used up or evaporate, right? As they leave, they pull the other ones up with them because of the cohesion. Now think about that. You're talking about, well, depending on the size of the tree, it could be hundreds of feet tall. So in some cases, that's really, really impressive. And it's all about the cohesion of water. That's it. That's the only force at work. And it's a force going against gravity, right? So it's a pretty strong force. Anyway, any questions about that concept or this picture? All right. Cohesion also gives us surface tension. Surface tension is the measure of difficulty in stretching or breaking the surface of a liquid. put a question mark next to that. I probably am not going to ask you that, but there it is anyway. Yeah, surface tension. And obviously that can be important for animals like this, right? Sometimes things need to walk on the water. Like that thing is. It's not floating. It's literally on top of the water, right? It hasn't displaced water. It's just on top of it. It hasn't broken the surface. Anyway, any questions about what surface tension is? All right, it's a great picture of surface tension. Well, it's not great. It's a good one. What's hard to see here is the water level is right about here. Right, that's where the water level is. So this Olympic swimmer is just about to surface, and the photographer got a really good timed picture. So they're above the water line, but they haven't broken the surface yet. So again, just another great example of surface tension, the cohesion of water. Any questions? It's another picture of surface tension. I like that because we are jackets. It's WVSU thing. Anyway, the second one, temperature, right? Water can moderate temperature. You need to know that. How many of you have ever done or seen it done where someone's cooking on the stove, and when they're done, they've got a hot eye, so they put like a tea kettle on there full of water? No one? Anyway, that's what we do. The reason being is because the water absorbs the heat. Here's something you don't, well, I don't know. We'll talk about this in more detail later. But one thing I haven't mentioned yet is what heat really is. At the molecular level, like right now, I'm going to say, what is it? It's 68 degrees in here. If I turn it up to 72, on the molecular level, does anybody know what's happening to the air molecules? If it's getting hotter in here, what's happening to those air molecules at the molecular level? They're moving faster. Good. That's something you do need to know. Remember that. So heat, as far as we're concerned in this course, is movement. It's movement energy, kinetic energy. It's a word I'll give you in the later chapter. It's all about movement. So think about that. The faster the molecules are moving, the hotter they're getting. And here's where that cohesion comes back into play, these hydrogen bonds. So picture, if you will, if we were to all stand up right now, we won't do it. If we were all like holding hands, and I said, all right, now that we're all here and holding hands, I want you to just wiggle around as much as you can. Now, you could wiggle around a lot, and things would get heated, right? It would warm up a little bit. You get warm from moving around. But you're holding your hands, so you can't move around that much. But if you just kept moving and moving and moving, like you're just getting stronger and stronger and putting more force into it, eventually you are just going to break your bonds, so to speak, and you won't be holding anyone's hand anymore. Then you can really move around. Does that make sense? So you're spinning around and running up, down the stairs, whatever. That's sort of like water molecules. Water molecules, when you heat them up, they do move around. They start wiggling more, and they try to spin, but they're bonded to each other. They have those hydrogen bonds. So even though you're adding more energy to it, and they're starting to move around a little bit, they can't move around that much because they're stuck to each other. They have those hydrogen bonds. So you keep adding heat, and it just keeps absorbing that temperature, and it keeps absorbing that heat, and the water temperature doesn't even change that much. You might not notice it because, we boil water all the time. So we think of water as something that's kind of easy to change the temperature because we do it when we need to cook. But physics, when it comes to physics, we're talking about it from that point of view. Water is actually really hard to heat up. So yes, that's why water is really good at moderating temperature, right? Because it has those hydrogen bonds. So you keep adding energy to it. And until it breaks those bonds, the temperature is barely going to change. Anyway, that's a really important concept, especially later in the semester. Especially, I would say, Bio 108 for those of you who have not had it. Because when you talk about different biomes of the Earth, this is what makes some of these places on Earth different. Like if you're on the coast, you see less temperature fluctuations than you do if you're in the middle of a continent, for example. Anyway, we're going to talk a little bit more about this concept, but are there any questions about this slide? Okay. So again, because of all those things I just mentioned, water moderates temperatures, and because of that, the temperatures can stay within the limits of life, right? So life as we know it wouldn't be the way it was without water, right? It could be too cold, it could be too hot. Anyway, I'll give some more examples here on the next slide. Are there any questions about this slide? All right, so there's also evaporative cooling, aka sweating. One of you has already written a paper about that. Let's talk about this very quickly. Sorry, really quickly. West Virginia is right about here, and London's right about here, right? So you can see London's a lot farther north than West Virginia, right? But if you look at the weather for those two different places, you would find out that they're actually quite similar for the climate. And the reason that is because Great Britain, right? That's on the water basically. It's an island, right? So it's surrounded by water. So we have all this hot air from the equator. It's moving this way for reasons we don't even get into in this class. It hits this continent, therefore it kind of curls up and it moves up towards the north. But as it's moving up towards the cold north, it still retains that heat that it got from when it was in the equator. And by the time it curls there and hits Europe, it's still relatively warm. I mean, it's not warm, but it's relatively warm, right? So that's part of what regulates the temperature. And Larissa, you're from Finland, right? What's the weather like there, the climate? Is it drastically different than ours? A lot colder?
Yeah, especially like in Finnish Lapland, which is like very northern, like up there. It's very cold, like very, very cold.
Yeah, right up here, this area?
Yeah, and the winter is lasting around like, I would say 7 months or so. So it's like kind of long winter. But as I brought to my independent work, like I've been seeing that like what the winter was when I was a kid, you have to definitely like change it because of the climate change.
Yeah.
Like the winter is not that cold anymore. But I mean, it's still cold and lots of snow, but like I think it used to be like longer.
Yeah.
But we also have very nice summers, like they're very warm and like beautiful summers.
Huh.
It's not like snowing all the time.
Right, yeah.
But like winters are very cold, very different than here.
That makes sense, because not only are they farther north, but that current that I was talking about, it does this. It circles like this, right? So that current, as far as I know, I don't think it goes up there. Anyway, just an example. Obviously, I'm not going to ask you any questions about that, but the idea, again, is that's how powerful water is as far as like moderating temperature. Also, obviously, that's a picture of a desert. How many of you guys have been to a desert? Nobody. Maybe? Okay. Well, some deserts, very often, especially depending on the time of year. All right, well, first of all, let me ask you this. What temperature do you think of when you think of a desert? Me too, and because it usually is, right? So very often during the day, it's really hot because there's no water. So you're getting all that solar energy hitting the ground, and there's no water to absorb the energy. So it just gets really hot, right? But then at nighttime, the sun goes away, and there's been no water absorbing that energy to slowly release that energy at night, so then it can get really cold. There's definitely exceptions to that rule, but that's how that works. That make sense? All right. And again, those are all just examples. I'm not going to ask you anything specific about that. The idea here is that water can moderate temperatures, right? And the reason water can moderate temperatures is because those molecules are hard to break. Anyway, and there's some evaporative cooling, right? So that person's sweating, and you can see it coming off. All right, another one. This is the other one that you need to know about. Ice floats. You need to know ice floats. You need to know why ice floats. And you need to know why it's important. So when water molecules get cold enough, they move apart, and that forms ice. So ice is less dense than water, therefore it floats. And that's an interesting thing, because most things, when they get colder, they get smaller. They get more dense. Right? Ice, water, on the other hand, when it freezes, it becomes less dense, and that causes it to float. So that is a natural, I won't say rare, but it's not a normal thing. And even for your own knowledge, not that you need to know this much detail, but water, it actually does. As it gets colder, it does get more dense. It does get more dense until finally it hits the freezing point. And then it hits, it gets the shape that I'm going to show you on the next slide. And then it's less dense. But even then, the ice, as the ice gets colder, it too becomes more dense. But anyway, what you need to know for the exam is ice floats. The reason it floats is because it's less dense. Another way of saying that it's less dense is the molecules have moved farther apart. I think that's how it's worded in the study guide. Has anybody done the study guide yet and can remember the wording for that question? Nope, that's okay. Anyway, yes, water can float because it's less dense, because the water molecules have moved apart. The reason they moved apart, it's just what they do, right? When they get cold enough, instead of, I don't know if you can see in this picture, it looks blurry, and it looks blurry for a reason. It's not because this is a bad projector or a bad picture. It looks blurry because what's they're trying to indicate is these water molecules are moving around, right? They're not sitting still. But then once it gets cold enough, which is 0 degrees Celsius, 32 degrees Fahrenheit, they get this shape and they stay there. They don't wiggle around anymore. They just stay in that shape. So that's why it floats. But that's also why it's important. Because it floats, let me see if this is on the next slide. Sorry, I don't remember it. Yeah. As the body of water cools, an ice layer forms on the top of it. And I know this sounds weird, but that ice layer acts as a blanket. Excuse me. Which I know it sounds weird because when you think of ice, you think of cold. But it's all relative, right? So yes, it's frozen up top, and yes, ice is cold. But then think again, like the Arctic Circle, for example. It's really, really cold up there, right? Really cold air. But there's that layer of ice, and below that, it's cold water. The ice is cold too, but it's not as cold as the air. So that keeps the water under the ice from freezing. Does that make sense? It really is a blanket. It's a blanket protecting it from the cold air. Yes, it's ice, and ice is cold, but it's not as cold as the air. And that's why it's so important. Without it, everything would freeze solid, and we just wouldn't have life as we know it. An example, not that you need to know this, if you download the PowerPoint, you can click on this slide. Actually, I made this last semester, and I don't remember if it's a video or a news article. But anyway, I used to live in Florida, and occasionally they'd have bad freezes, and they would see, you would usually see them coming. And when the farmers, the orange farmers, saw them coming, they would spray all the trees with water. So it sounds counterintuitive, but it's the same concept. They spray the trees with water. The freeze comes in. The trees are covered in ice, which again sounds cold, but the ice is relatively relatively warmer than the air. So that ice is blanketing the tree and protecting it. Anyway, any questions about the biological significance of ice floating? All right. And then the last of the 4 reasons that water is important for life. Water is a solvent. This is a concept you're definitely going to need to know. We're talking about it in this chapter, and then we're going to talk about it again, I think 2 chapters when we talk about diffusion and talk about cell membranes and things coming in and out of a cell. So these are terms you definitely need to know. Solution, solvent, and solute. Solution is a liquid with two homogeneous mixtures of 2 or more, with a homogeneous mixture of 2 or more substances. Now, this is a 100 level class, so if you're taking notes or making flashcards to study, you really could shorthand this and just put solution is a liquid mixture, right? That's probably going to suffice. That'll suffice for this class. I'm not going to add, yes, it's homogeneous, but I'm not going to use that in the exam. You just need to know the solution is when you've mixed a bunch of stuff together. Specifically, what you've done is you've dissolved a solute in a solvent, and that gives you the solution. So that's what you need to know, right? You dissolve a solute in solvent, and that gives you a solution. Most likely in the exam, I'm not going to ask you the definition. Most likely I'll give you some kind of example and say, I put salt in the water to make salt water. What is the solute? And in that situation, the salt was the thing I dissolved, right? So the salt was the solute. And I would say, what was the solvent? And you would say, the solvent was the water. The water is the thing that dissolved the salt. And then I would say, what is the solution in that situation? And you would say, the solution was the salt water. Does all that make sense? All right. Now, again, water is a good solvent. Obviously, since we're talking about water being a solvent, there is this term called an aqueous solution. But I'm not going to ask you what an aqueous solution is. As far as we're concerned, the only solutions we talk about, I think, are aqueous solutions. Anyway, the next word for attendance will be cat. So again, just normal thing for those of you who are here. If you want to, send me those words before 9 a.m. for a little bit of extra credit. If you're online watching the live stream right now, you need to send those words before 9 a.m. for your credit. And if you're watching the video at a later date, send me a picture of that cat. No, I take that back. Of any cat. Send me a picture of any cat. Anyway, any questions about this slide? So again, you need to know this relationship between those words. solvents dissolve solutes, and that makes the solution. That will be important later in the chapter, in the semester. Water can dissolve a variety of solutes and provides a medium for chemical reactions. In other words, basically, almost all of the chemical reactions that are happening in our body, which we wouldn't be alive without them, happen because of water. Right? Because water dissolves stuff. I'll give you a good example on this next slide. This. So here we have sodium chloride. Guess what? That's what it looks like. Your body doesn't need sodium chloride. It does not use sodium chloride. It uses sodium. It uses chloride. The salt itself, the stuff that you eat, it doesn't need it. That's where the water comes in, right? So the water has to dissolve this because we do need the chloride. We do need the sodium. But without the water dissolving it, it's useless to us, right? It's just sodium chloride. So any questions about that? That's just an example. You don't need to know specifically about sodium and chloride. But that is a really good example of how water can dissolve it and how without dissolving it, it's completely useless. Any questions? Excuse me. Any questions about this slide? All right. Acids, we won't jump into that. We'll stop here 2 minutes early. Yeah, that'll be it. We'll talk about acids and bases when we get back on Wednesday. And also, if you have lab today, we'll talk about it in lab today. And that's it. If you came in late, make sure you send me an email that says you came in late.